I would like to introduce a concept that will make things much easier when it comes to comparing the efficiency of different data structures. As developers, we need a common language when we're expressing how efficient the data structures and all the operations we're working with are. That metric exists, and it is called Big O. All that Big O tries to answer is this: if I have some data, as that data grows, how much will the computer operations grow? This is because computational power is never cheap. Every single operation your computer performs comes with a cost. And we need to know how much these operations are going to cost so we can choose the cheaper and the faster data structure. By the way, if you're lost when it comes to the operations, don't worry, we're going to clarify that in a minute. Welcome to DSA, the series that teaches you exactly what you need to master data structures and algorithms. Okay, so let's make an analogy so you can understand this clearly. You work in a library and someone asks you to find a specific book. In the first scenario, the books are spread randomly on the floor and you start checking them one by one. If there are a million books and you don't have any luck, you check a million times. In the second scenario, the books are organized alphabetically on shelves. If you go to the middle shelf, decide whether your book comes after or before, eliminate half the books, and repeat. With a million books, you find it in about 20 steps. Okay, so now imagine we double the library to 2 million books. Now you need 21 steps, barely more. In the third scenario, every book has a unique code and there is a system that gives you the exact location of the book. You enter the code and go directly to the shelf. It doesn't matter if there are 10 books or 10 million, you find your book in just one step. Okay, now let's see how BigO works and the different labels or complexities we have when we want to classify a problem. Okay, so first we have constant time, meaning it doesn't matter if you have 10 elements or 10 million, it always takes the same number of steps. As an example, we have accessing an element in an array by its index. When you want the element at position 5, the computer calculates the memory address and goes directly there. It always takes one step. Logarithmic time, each step cuts the problem in half. Instead of checking items one by one, you eliminate half of the remaining choices with every move. At each step, you eliminate half of the problem. That means you can search through millions of items in just a few steps. A real-world example will be guessing a secret number between 1 and 100. Instead of guessing 1, 2, 3, you guess 50. If the number is too high, you cut the work in half instantly. A range of 100 numbers takes only 7 steps. A range of 1000 takes only 10 steps, and so on. Linear time is actually pretty easy. The operation grows in direct proportion to the input. Double the input, double the work. As an example, we have printing a list of usernames onto the screen. If your database has 5 users, we print 5 times. But if your database has 5,000 users, the computer must run that print command 5,000 times. Then we have quadratic time, and I recommend you to avoid this because for every element you have, you must interact with every other element. And if you double the amount of data, the computer does 4 times the steps. Now that you know what the complexities are, I want you to go back in the video and try to classify the 3 scenarios I just gave you, and put them in the comments if you think you got them right. Now take a look at how these complexities actually work for 1 million elements. If you notice, the difference between logarithmic and linear time at scale is the difference between 20 steps and a million. Now check that the difference between linear and quadratic time is the difference between a million steps and a trillion. A wrong choice under scale doesn't make your program slow, it makes your program stop working entirely. For every structure, you need to understand what is it optimized for and what does it cost. This is extremely important for you as a developer, so bear with me. Let's start with the list branch. A list keeps things in order and lets you access them by position. Inside the list branch, we have ArrayList and LinkedList as the most important data structures. An array is a block of computer memory where all elements are stored next to each other. Because the computer knows where the array starts and how much space each element takes, it can calculate the exact location of every element and go straight there. Tell me in the comment if you want a whole video talking about what happens underneath this process. So if the computer goes straight to the value we want, what do you think the time complexity of that operation will be? Yeah, exactly, constant time. It doesn't matter how big the array is, it just takes one step to get to the position where the element is stored. Okay, so since every value reference is stored directly next to each other, if we want to insert a new value in position 3, for example, but the position is already occupied and so is every space after it, what do you think is going to be the complexity of shifting every value from the position 3 onward to make room? You've got it right, it's linear time complexity. Every value from the position 3 onward has to move over by one spot. If the array has 1000 values, you may have to move 996 of them. So you already know that an array is a given fixed amount of memory when it's created. If it fills up completely and you try to add one more value, there is not extra room right after it. The memory already belongs to something else, so what do you think has to happen to fix the value we're trying to insert? The complexity of all this work is also linear time. If you know why, let me know the reason in the comments. Now that you understand ArrayList completely, let's see a structure that exists specifically to fix its biggest weakness, the linked list. A linked list doesn't store its values next to each other in memory. Instead, every value lives inside something called a node, and each node holds two things, the value itself and a pointer. Think of a pointer as an address that tells where the next node lives in memory. That basically means the nodes can be scattered anywhere in memory. Node 1 may be at one address and node 2 somewhere completely different. They are only connected because each one knows where the next one is. Now think back to the array problem. If I want to insert a value between node A and node B, which of those do I actually have to move? That's right, none of them. The only thing you gotta do is create a new node anywhere in memory, point it to B and update A to point to the new node instead. Alright, so what do you think the time complexity of inserting here is? Exactly, costs some time. It doesn't matter if the list has 10 nodes or 10 million, it is always just two updates. But wait a minute, let's analyze this. If I have an array and I ask for the value in the position 500,000, the computer calculates the address and goes straight there, right? But with a linked list, I cannot do that. The computer only knows where the node 0 is. So what do you think the complexity of accessing by position in a linked list is? Exactly, linear time. So look at this, a write and linked list have the exact opposite trade-off. One is O1 to access and ON to insert in the middle. The other one is ON to access and O1 to insert, but once you're there. Same problem, but you have to choose each one depending on the operation you're going to perform. Now let's open the set branch. Remember that a set doesn't care about order or position. It only cares about whether a value exists or not. The first implementation we have here is HashSet. HashSet takes the value you want to store and runs it through something called hash function, a formula that converts the value into a number. That number tells the computer exactly which slot in memory to put the value in. So later, when you want to check if the value already exists or not, what do you think the computer does? Exactly, it runs the value through the same hash function again, gets the same number, and goes directly to that slot. So what's the time complexity of checking if something exists in a hash set? Since position is determined by a formula, not by when you add something. If you want to print the elements, what do you think happens to the order of the elements when you loop through a hash set? It comes out in a meaningful order or not? So what do we do if we actually need our unique value sort? The response to this is a tree set. A tree set doesn't use a hash function. Instead, every value goes into a tree structure where there is a rule. Anything smaller to a given value go to its left and anything bigger go to its right. So if I want to check whether a value exists, what do you think happens? Does the computer go straight to one slot like a hash set? No, right? It starts at the top of the tree and compares. Is my value bigger or smaller than this one? And it moves left or right based on the answer and repeats. What complexity does that sound like to you? Logarithmic time, isn't it? See that you're catching up now? We just lost the O1 access we had in the hash set, but in exchange we gain order. We can loop through a tree set and get every value in order from smallest to largest automatically. We can even ask, give me everything between 40 and 60. Something a hash set has simply no way of answering. Because in a hash set, there is no relationship between where a value is and its actual size. Now let's move to the queue branch. A list is about position, a set is about uniqueness, a queue is about processing order. So let's start with ArrayDeque. An ArrayDeque follows this pattern. Whatever element got added first is the first one that comes out. So if I add A, then B, then C, and I remove from the front, A comes out first. That is called FIFO, first in, first out. Think about a line of people waiting to enter a store. The person who arrived first gets handled first. It does not shift every other element to the left like an array list, which as you know is pretty expensive. Internally, it keeps track of where the front and the back is. So when you remove from the front, it doesn't have to move all the values. It just has to move the front marker forward. And when you add to the back, it already knows where the back is. Alright, so what do you think the complexity is here? Exactly, O1, linear time. And not only that, an array queue is even more flexible than a normal queue because the queue means double-ended queue. That means you can add or remove from both sides. But now let's change the question. What if the importance of the elements matters more than the order? That is where priority queue comes in. A priority queue does not process elements based on who arrived first. It processes elements based on priority. Think about a hospital emergency room. One person may arrive first with a small headache. Another person may arrive later with a serious emergency. The second person is going to always get handled first because they have higher priority. What happens when I remove it? The heap has to reorganize itself to figure out which value becomes the new, most important one. The reorganizing process costs logarithmic time. It is fast, but not free like just looking. The last world is the world of maps. Remember, a map is not about storing values directly. It's about storing a key that points to a value. The first implementation we have here is a hash map. And this works almost exactly like a HashSet, except now the hash function is applied to the key, not to the whole value. The key gets converted into a number, and that number tells the computer exactly which slot the value lives in. So if I want to retrieve the value for a given key, what do you think the computer does? It hashes the key again, gets the same number, and goes straight to that slot. The complexity of all this is, yeah, constant time. If you look close, it's the same reasoning as HashSet, except now it is applied to a key value pairs instead of single values. And just like I said, what do you think we lost with a hash map? The same thing we lost with a hash set, order. It happens that the keys come out in no particular sequence when you loop through it. We use the same fields as before, a TreeMap. And yeah, a TreeMap stores keys in a tree structure instead of hashing them. Smaller keys go left, bigger keys go right, just like a TreeSet. So what do you think the time complexity of get and put becomes here? Logarithmic time is slower than a hash map's constant time, but in exchange, we get keys in short order automatically. And we get the ability to ask range questions like, give me every key between 100 and 200, something a hash map simply cannot do. Okay guys, if this episode helped you, make sure you hit that like button. See you in the next one.